Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on August 28, 2025, which was about 7 days ago. The standout result is simple and striking. Replacing local gradients with layer-wise relevance propagation boosts faithfulness so much that for MLP outputs in GPT-2 Large, attribution patching gets a Pearson correlation of 0.006, while relevance patching reaches 0.956. The paper is titled RelP, Faithful and Efficient Circuit Discovery via Relevance Patching. And as we will see, the efficiency and accuracy both move in the right direction. The method matches integrated gradients level faithfulness while keeping 2 forward and 1 backward pass efficiency. On X, a co-author announces the preprint, contrasts noisy attribution patching with costly integrated gradients, and claims RelP combines speed and faithfulness, showing supportive bar charts and modest engagement at roughly 80 likes. Alright, the previous segment highlighted headline numbers. Figure 1 now shows the full comparison across model families and components. The 3 bars groups report Pearson correlation with activation patching for attention outputs, MLP outputs, and the residual stream, so taller yellow bars mean closer agreement. Across Pythia, GPT-2, QN2, and Gemma 2, the yellow RelP bars consistently match or exceed blue attribution patching bars. The gap is widest for MLP outputs and the residual stream, which confirms where gradients were least reliable. So, while the previous figure contrasted faithfulness across models, Table 1 summarizes the propagation rules that make the relevance signal stable and sparse. The table lists layer norm, activation functions like GELU or SILU, linear layers, attention, and multiplicative gates, each paired with an LRP rule and a simple implementation trick. Treating certain terms as constants during backprop helps conserve relevance, which reduces noise. These rules matter because RelP depends on accurate propagation coefficients to replace shaky local gradients. Alright, Table 1 just detailed the propagation rules that keep signals clean. Figure 2 presents a qualitative side-by-side for GPT-2 Small. The left column shows activation patching heat maps, the middle shows relevance patching, and the right shows attribution patching, each split by residual stream, attention output, and MLP output. The middle column closely mirrors the left across layers and positions, which indicates faithful alignment. The right column drifts, especially in the residual stream and at MLP 0, so gradients mislead there. Well, Figure 3 tracks circuit quality as the number of nodes increases, which directly tests whether small circuits capture model behavior. The top panel shows faithfulness rising quickly and flattening near 1 for feature circuits, with RelP matching integrated gradients despite lower compute. The bottom panel shows completeness dropping towards 0, so the remaining model explains little once the circuit is active. The legend distinguishes RelP and integrated gradients for feature and neuron circuits, including versions without sparse autoencoder errors. So, the previous figure contrasted qualitative alignment. Table 5 reports the exact Pearson correlations with activation patching across components and model families. The table shows that relevance patching beats attribution patching in almost every cell, with the biggest gains for the residual stream and MLP outputs. GPT-2 Large illustrates the contrast, where attribution patching drops to 0.006 on MLP outputs, while relevance patching reaches 0.956. These numbers confirm that the LRP-based propagation produces far more faithful estimates at the same compute cost. Okay, 2 takeaways stand out. Replacing local gradients with layer-wise relevance propagation yields activation patching level faithfulness at attribution patching level cost, and the gains are largest for MLP outputs and the residual stream. The broader implication is faster, more reliable circuit discovery that scales to bigger models. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.